So we're recording. Next, what are we talking about? This is chapter 5. What am I going to use for notes? I'm literally going to be looking at my study guide here with you guys. Okay, so the topic is chemical equations and chemical reactions. That's what this chapter is all about. What is a chemical equation? Chemical equation is defined for you right there. It's an expression with symbols and formulas to represent the chemical reaction. Okay? You can think of a reaction. So reactions are changes in chemical structure. Reactions are changes in chemical structure. Equations are essentially symbolic representation of that. Using formulas, symbols, numbers to explain what is going on. It's a way to literally describe the chemical reaction. Okay. If someone says to me, "You're burning methane gas," so burning methane gas, what does that mean? That means combustion of methane. Methane is CH4. Okay, there's a bunch of things that you guys are going to have to learn to be able to do that. To begin with, I'm not going to expect you to know what methane is explicitly, but I might say the burning of CH4 or carbon tetrahydride. Carbon tetrahydride is methane gas. Combustion, we'll get to that under the section that actually talks about types of reactions. That's 5.2. Right now, we're not there yet. Okay. What does that mean, though? CH4 plus O2. That's what a combustion reaction is. I'll redefine that for you real quickly in a second. But the products of this are going to be CO2 and H2O. Okay, this is a basic chemical equation. Now, you can see what a chemical equation is. It is describing the reaction. It is saying carbon tetrahydride reacts with diatomic oxygen gas to give you carbon dioxide and water. That's the basic thing we're talking about here. Any questions so far? Okay. This, however, is missing a lot of information. This is just a very simple, basic chemical reaction. What's missing from that a balanced reaction, and I'll explain that to you guys in a second. And the phases, liquid, gas, solid, of the substances. Okay? before we even talk about balancing, let's talk about phases. Phases matter. Bad pun. Phases are important. It's vital that you know what the phases are. There are actually 4 phases that we care about. So phases are important because they indicate what is actually going on. What is actually going on with regard to the energy and interaction of stuff. We're going to start with a very simple term, stuff. Okay, so what are those phases? Liquid, gas, solid, and aqueous. Liquid is going to be represented by the letter L in parentheses. As a subscript after the formula. Same goes for all of these. Gas is a G, same location. Solid is going to be an S, same location. And aqueous is going to be AQ. Same location. Now, in general, you guys, I think, know what are solids, liquids, and gases. Does anyone want me to review those briefly? I'm happy to do so. That was chapter 1. If phases, solid, that's the 3 primary phases, solid, liquid, and gas, is anything that you aren't certain about, review those in chapter 1, please. Aqueous is a new phase. Aqueous means dissolved into, anyone know? Some dissolved into water. Water is solvent, dissolved means homogeneously mixed into. It doesn't mean it's settled to the bottom like it would if you were looking at a balsamic vinaigrette or a stew or muddy water, which if you leave muddy water alone long enough, it'll just settle to the bottom. That would be a heterogeneous mixture. A homogeneous or homogeneous mixture is going to be always perfectly evenly distributed throughout, like salt water. You take salt, you mix it into water, it just dissolves in. Sugar water, it just dissolves right in. Okay. Any questions? All right. Now, if there are no questions here, the next thing we need to talk about are the influence of the conservation of mass, which is a law, and the reason we do, and how to balance equations. This is very simple when it comes to the idea of conservation of mass. The quantity of mass meaning number of and number of each type of atom input must be equal to the mass quantity number of and type of output. Input must be equal to output. The number of each atom of each element into the equation must be equal to the number of and quantity and type of element out of the equation. That must be the case. Input must be equal to output. We're not doing nuclear chemistry here. The only place you can change what an element is, or you can change and have different elements present, is nuclear chemistry. And we're not doing that. So that's the reason we do it. It's the conservation of mass. How do we do it? You cannot change the symbolic formulas of the reaction. To change the formula is to change the compound, is to change the molecule, is to change the formula unit, is to actually change the input. You cannot do that. You cannot alter the molecular formula or molecular formula when it comes to covalently linked atoms in a molecule, or the formula unit if it's an ionic compound. If it is a pure element, you use the type of pure element. And with a few exceptions, that usually is just symbolically one atom. There are some exceptions to that. Sulfur and phosphorus have unique types of structures associated with that. For example, phosphorus has two different forms, one of which is just P5. But if that were the case, I would give that information to you. You do not need to memorize the special cases normally. Cases that you do need to know. Elemental diatomic gases. O2. If I say elemental oxygen, it's O2. Elemental diatomic gases. O2. N2 is elemental nitrogen. H2 is elemental hydrogen. And then you have the halogens. F2, Cl2, I2, and Br2. And there's only 7 of them. And they even make a 7 on the periodic table. Well, okay, 6 of them make a 7 pointing at the 7th. You start with nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There's the 7 pointing at hydrogen. 6 of them make a 7 pointing at the 7th hydrogen. Okay, there you go. It's even built into the periodic table. Any questions? Okay. Aside from that, normally for metals, you just do something like iron, solid, silicon, solid. Okay. Or solid nonmetals. Most are just things like carbon, solid. Yeah, P5 is one that will be given to you. The ones that I would expect you to know are the ones that are normal. Understand this idea and this. I'm not going to give you the, I'll give you the weird ones. Yes. Yes, I am expecting that. Exactly. That's why I'm even going to show you here, gas, 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 and it should actually be kind of lower here. And aqueous. Don't forget the fourth one. Aqueous is another one that you are responsible for. Okay. Good so far. Okay. Next thing. So I'm just going through this. Okay. On an equation, you guys have seen this before. Chapter 1. You have the reactants on the left-hand side. Arrow. You have products on the right side. Okay. The next thing to keep in mind will be if we use capital letters to represent the formulas of substances and lowercase to represent coefficients. Oh wait, what's a coefficient? Sorry? Well, yeah, you absolutely can look in the study guide. I'm pretty sure coefficient is in there. It's even defined for you. And it's okay if you read from that. Part of the reason I gave it to you. Get you guys in the habit of using it as a reference. Okay? I don't mind if you do that. What does it say? It says it's a number placed in front of a formula to balance a chemical equation. Okay? In extremely general terms, coefficient is a constant numeric value that multiplies into a symbolic representation of something. In algebra, the symbolic representation are variables, x, y, other letters. The coefficients are the constants to the left of or in front of those variables. In chemistry, in chemical equations, the coefficients are still numbers. We generally use whole numbers. We don't generally use fractions. We generally use whole numbers. We normally use whole number integers to balance the equations. Any questions? It's better to see what this looks like than to just talk about it. I can give you definitions till the crows come home. I don't even know what the crows are or who they are. But definitions don't give you examples. Examples help. So does anyone need more time? Definitions are right here. You got the study guide. This is what I'm referencing. Okay. So let's look again at CH4. Methane is going to be a gas. We're going to add to it oxygen gas. This is a combustion reaction. Combustion is the reaction of a substance with diatomic elemental oxygen to produce, the general products are oxides, things that have reacted with oxygen and now have molecules that have oxygen in them, and heat. So carbon dioxide gas, that's carbon with oxygen, it's an oxide. And people don't often think about this in their day-to-day lives, but H2O is an oxide of hydrogen. It's hydrogen with oxygen. That's also going to be a gas. So now you look at this equation. Okay. You can go through the balancing of an equation notes there. I'm not going to go and write these all out because they're right there for you. So rather than writing them out for you, I'm going to say reference the study guide if you want to go through the steps. I'll just kind of go through them for you. You write the unbalanced equation using the correct formulas for all reactants and products. There we go. You make sure that the subscripts and the chemical formulas do not get changed. You do not alter the molecular formulas. You do not alter the formula units. You keep the reaction as it is. The only thing you can do now are add coefficients. The only thing you can do is add coefficients. Everything here by default has a coefficient of 1. All you can do is increase the coefficient. So you can do this if you want. You can create for yourselves a elemental track sheet, if you will. Carbon, hydrogen, oxygen, those are the elements I'm tracking. Okay. You can create a little table for yourself even. You can go reactant side, product side. There's different ways of doing this. You can do it like this. You can go carbon, hydrogen, oxygen, and have the reactants on the left side and the product side. There's different ways of doing it. Doesn't matter how you do it. Just use it as a tool if you like to track these things. To start with, carbon on the reactant side is 1. On the product side, we've got 1. You can see CH4 versus CO2. There's 1 carbon on each side, 1 and 1. Now, hydrogen is the next element I'm going to look at. There's 4 of them here on the reactant side. You can see they're present in the methane, nothing in the diatomic oxygen, of course. So there's 4 there. On the other side, I've got 2. So there's 4 and 2. Finally, oxygen. I've got 2 on the reactant side, and I've got 2 plus 1 is 3 on the product side. 3. Now, I can only change these things by adding coefficients to the symbolic formulas. I can only alter things by putting coefficients in front of the formulas. Therefore, what am I going to do? Well, the last thing I want to change is something that only has 1 element. Here's a hint. Generally, save anything that is elemental, like the pure oxygen, to put a coefficient there last. Because the easiest thing in the world to do is to alter something that is just by itself. If I put a 2 in front of this CH4, that means now I have 2 carbons and now 8 hydrogens. Okay? If I put a 2 in front of this oxygen, yes, I've got 4 oxygens, but that means I've only changed the number of oxygens. So save the elemental thing for last. That will be the easiest to balance. Start with something that's harder. The next thing I do is I look for something that's easy to alter as far as numbers go. I've got 4 hydrogens versus 2. Why don't I try to put 2 hydrogens on the other side? Okay, I have to do that by putting a 2 here. So I put a 2 next to the water. I track that now. This has now become 4. But you can see this has also changed and affected the number of oxygens. So I've now gone from 3 to 2, and 2 is 4. So my oxygens now is 4 there. Okay, that makes sense? Now I happen to prefer this bottom table because as you build out from it, it's easier than this table here. Track it how you like. I happen to prefer the bottom one, just my personal preference. Do you see how these things have changed so far? Okay, we've now still got 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, 2 oxygens on one side, 4 on the other. Now hopefully you can see this is very straightforward. The last step you need to do therefore is put perhaps a 2 right here. 2 times 2 is 4, giving me 4 oxygens on that side. Now you can see it's 1 and 1, 4 and 4, 4 and 4. And this is my finished balanced equation. This is my balanced chemical equation. You can very easily check it with your tallying down here at the bottom. By tracking that, you can have more confidence in your balanced equation. But you have to track it accurately. Keep that in mind. You must track it accurately. Any questions? Yes, these get more complicated. This is a simple example. This is a very simple example. They definitely get more complicated. Any questions? Make sense? Okay. In many ways, this is an easier topic than quantum mechanics. This is an easier topic in some ways than some of the stuff we've done earlier in the class because this is tangible. This is right in front of you. Okay, if there are no questions, I'm going to move forward. Then, we just talked about balancing equations. I've shown you an example of balancing equation. Next thing, let's talk types of reactions, which is section 5.2. This honestly is a section that really you can read. But I'll show you a few things, okay? Classes of reactions. So you've got the combination, it's called combination, which another way of thinking about it is you are combining things. This is also called a synthesis reaction because synthesis occurs when you combine things. You build larger things from smaller things. You do something like x plus y giving you xy. Okay, calcium plus sulfur giving you calcium sulfide, like the example in the study guide. Next, so if that's combination, then you could definitely say that there is a opposite of that, which is decomposition. This is literally what it sounds like, breaking things down. Okay, this is breaking things down, decomposition. We know that typically when people think of decomposing things, they think about rotting things, things that fall apart, things that decay. Honestly, that's what's happening. You've got decomposition reactions going on. You're breaking stuff apart. You literally are taking something like the opposite of this. You're going x, y, and you're breaking it back into x plus y. For example, there, you're taking calcium 2 oxide, and from it, you're getting solid calcium and diatomic oxygen. Again, I'm referencing the study guide here. Okay. Any questions so far? These are definitions. What you need to be able to do is take these definitions and recognize the type of reaction. Just like in the assignment, page 1 of the assignment that I've handed you, and page 2 are all about balancing equations and recognizing the type of reaction. First 2 pages of that assignment do exactly that. Recognize the type of reaction, balance the equation. Okay. That's decomposition. Next, we've got displacement. Displacement is exactly what it sounds like. It is displacing something. It is something like A plus BC. So this is A by itself plus BC, giving you AC plus B. Another name for this reaction is a single displacement. Really, we should call it a single displacement or single replacement. Or you could call it an exchange, a single exchange reaction. And yes, I will sometimes use RXN to communicate reaction because I don't feel like writing out the word reaction all the time. Displacement or single displacement, single replacement is that. Then you have what we call the exchange reaction, just to get confusing. This is called a double displacement or double replacement. And I'm giving you all of these names because these are the different names you'll see in different textbooks or different references. Okay. This looks like AC plus BD, giving you BC plus AD. This is a cation, anion, cation, anion. They're exchanging dance partners, if you will. Okay. Note that in the single displacement reactions, this usually is something like a solid and something that is aqueous, typically, to something that is now aqueous, and now you form a new solid. You'll see this quite often in electrochemistry or plating of a metal. Which means, yes, you see this in the chemistry of batteries. This will be something along the lines of perhaps aqueous plus aqueous, and then you'll end up with something like aqueous and a solid. Okay. In this case, this is also called a precipitation reaction. Precipitation reactions are the formation of a solid. And yes, that solid is called the precipitate. It's all right here. Okay. The solid is called the precipitate. This is all here in the study guide. Good so far? Okay. I'm doing on time. Not as good as I wanted. Way behind. Okay. Last type of reaction. Here we go. Or no, last 2 types of reactions. Okay, so we've got 2 more types of reactions. Combustion reactions, which are, typically, you take a substance, which is usually some sort of carbon, hydrogen, or other stuff. You add to it. You'll always add to it diatomic oxygen, gas, and it will produce oxides plus heat. One of my favorite questions that I often ask on the first exam is, are flames matter? What is fire? What is fire? What are flames? They're not an element. They're just light and heat, and that is all. You cannot touch fire because fire isn't matter. It does not have any substance to it. Fire does not have any substance to it. It is just light and heat. It is just energy. And that is all fire is. And yeah, it hurts like hell because that is a ton of energy coming into contact with your body, causing those body parts, those molecules that you are built of, to fall apart. There is so much energy that it breaks the bonds that it comes into contact with, but it is just light and energy. Light is a type of energy, yes. It is just energy. So that's combustion. Finally, neutralization reactions. Neutralization reactions, you take an acid plus a base, and your products are going to be water, typically, and a salt. And when I say a salt, a salt, I'm not talking about a salt, I'm talking about a salt, and not just sodium chloride. A salt is an ionic compound. A salt is another name for an ionic compound. Any questions? Okay, these are just definitions, just the things right here. Just as a reminder, acids are going to be things that have a hydrogen and then an anion, like HCl, HC2, H3O2. This is acetic acid. This is hydrochloric acid. I don't have enough time to lecture in person. That's just not how this class works. It sucks. I'm sorry. Bases are going to be typically a cation and hydroxide. This is hydroxide, which is OH minus. I put it here with no charge because it's in a ionic compound. These are ionic compounds, and the bases are typically ionic compounds. The acids are typically not. Okay. So, balancing equations, types of reactions, pages 1 and 2. Next page, this is net ionic equation worksheets. Thankfully, this has some very straightforward explanations. So, this is now 5.3, because I'm really trying to get through some stuff here. Precipitation reactions and solubility. I'll have to come back to that because the point I want to get to is actually 5.5. 5.3 is precipitation reactions. 5.4 talks about acids, bases, neutralization. I am so far behind on time. 5.5 is where we want to get to. This is redox, and honestly, I think redox reactions are more challenging than precipitation reactions and acid-base neutralization. Those two topics, challenging. Redox, even harder. I'm just being honest with you. Okay? So we're going to skip to 5.5 because I want to talk about at least a couple of things. Good so far? Okay. Here we go. Redox. What does redox stand for? Well, it's actually two different words that have been combined. It's a combination of two words associated with two types of reactions. What are those reactions? Well, red for reduction reactions. What is the definition of a reduction reaction? The definition of a reduction reaction what could it be? Could it be is the gain of electron. Reduction is all about gain of electrons. Ox comes from oxidation reaction, which is all about loss of electrons. Note, I did not say anything about oxygen. Oxidation reactions do not require oxygen to occur. The only mention of oxygen here is to mention that it's not required. Good so far. Okay. What does that bring us to? That brings us to some silly little ways of trying to remember this. Memory tools. There's this one that is Leo Gur, like a tiger. Leo the tiger says Gur. Loss of electrons is oxidation. Gain, actually should be an E. Apparently Gur, the tigers say here is guerre. Guess they're French. Gain of electrons is reduction. Okay, so loss of electrons is oxidation, gain of electrons is reduction, Leo Gur. Or if you are more into petroleum products, you can use oil rig. Oxidation is loss, because this just talks about electrons. It's all about the electrons. Oxidation is loss. Reduction is gain. Loss of electrons is oxidation. Gain of electrons is reduction. Oxidation is loss. Reduction is gain. Oxidation is loss. Reduction is gain. Okay? I cannot emphasize that enough. Oxidation is loss. Reduction is gain. What are we talking about? It should be obvious. These reactions all involve the movement or exchange of electrons. We're talking about the movement or exchange of electrons. We're watching the electrons move. We're watching them be exchanged. That is what this is all about. Okay, so now you can see the generalizations there. Number of electrons lost or gained can be predicted based on the position of the element in the periodic table, blah, blah, blah. Tracking electron movement is how you tell if They've moved, because if you're watching the electrons and there's no electron movement, then, oh, there was no electron movement, there's no oxidation, there's no reduction. However, if there's movement, this is how you tell what lost electrons and what gained them. Because that's what we care about. We're trying to figure out, where did those electrons go? Did they go from this element to that one? Did they go from this element to that one? That's what matters. That's what we're actually trying to figure out here. So how do we track that? Well, it turns out that tracking them is something that we do kind of the way accountants do this sort of thing. So we're going to do this by tracking them the way that an accountant would. We track them with numbers. We track electrons with special things called oxidation numbers. Oxidation numbers. Okay. So what's an oxidation number? It is a tracking system. It is a number that indicates whether an atom is neutral, electron rich, or electron poor. Has it gained electrons? Has it lost electrons? Has nothing changed? It is an imaginary number, not an imagery number. I should say imaginary. It's the first typo I've really found in my thing there. Go ahead and fix that. Let's go ahead and do that together. That should say imaginary. Okay, it's an imaginary number. Oxidation number is not like a charge. A charge is a real thing due to a difference in number of particles. An oxidation number is not a real thing. It is a tracking system. Therefore, so it's an imaginary number used to track electrons. Electron rich, electron poor, no change, etc. Symbolism and meaning, symbolism and meaning are vital, which is, yes, why I bother with this next section. How you write an oxidation number matters. It is going to be charge followed by quantity, or also known as a number, the magnitude. It's going to be charge, then number. Remember that actual ionic charges are written the number value, then the charge. This is a difference. I do grade based on this. This is something important to me. Some chemists get lazy and they combine the two. That's not acceptable to me. That's like saying a chair is a table. They are not the same thing. You do not sit on tables when you're eating food. You sit in a chair, you put your food on the table, you eat. That is civilization. This is civilization. This matters. Okay? All right. So, how do we determine oxidation numbers? Rules for assigning oxidation numbers. This is on page 7 now. Okay. 1. Any elemental pure atom that is alone doesn't matter the number of pure atoms. As long as the atom is by itself, it's an elemental substance. We call these elemental substances, just like I was talking earlier about the gases, diatomic gases, phosphorus with 5. Doesn't matter the number of atoms. If it's a pure elemental substance with no other element different from itself, the oxidation number assigned to this state is 0. Cero. Ninguna cosa. Not a single thing here. 0. Not negative, not positive. 0. So, whether it is magnesium solid, whether it is carbon solid, whether it is mercury liquid, whether it is oxygen gas or nitrogen gas or phosphorus, 5 of them. I don't care. You could have something like what the hell? You could have palladium 10,000. I don't care if it's by itself. These all have the same oxidation number, and that oxidation number is 0. Okay? Straightforward? Makes sense. Pure elemental substances, doesn't matter the number of them. As long as they're alone, the oxidation number is 0. Next, rule number 2. A monoatomic ion has an oxidation number equal to the magnitude and positive, negative charge of the ion. This is hopefully a straightforward one as well. So, sodium 1 plus equals an oxidation number of positive 1. Magnesium 2 plus has an oxidation number of positive 2. See the difference. The charge is 1 plus, the oxidation number is positive 1. 2 plus is the charge, the oxidation number is positive 2. Chlorine 1 minus is an oxidation of negative 1. Phosphorus 3 minus, so the phosphide ion has an oxidation number of negative 3. Okay? This is straightforward. The only thing that has changed is the position of the charge to indicate the difference between a charge and an oxidation number. The sign has moved. The sign indicates whether it's an oxidation number or a charge. I could even change this to the appropriate word, the sign. The sign. Okay. Did I use that properly? Yeah, it's not charge. The sign. Positive and negative are signs. This is the sign. That's what it is. It's a sign, not a charge. It's a sign. Okay. In a molecular compound, rule number 3. Molecular compound total oxidation number sum must be, what do you think it must be equal to? Must be equal to 0. Compound means 0 charge. That also means total oxidation numbers must be equal to 0. Okay. That doesn't mean that the atoms within that have 0. In a non-elemental compound, in one that contains multiple different types of elements, as long as the electronegativity of the element exceeds that of hydrogen, which generally means as long as H is not paired with a metal, then H has an oxidation number of positive 1. If it is hydrogen paired with another nonmetal, hydrogen is basically positive 1. Okay? This is hydrogen in the company of another nonmetal. Okay, I'm going to move quickly on these because once we have these, I have to stop. Next, oxygen is almost always in substances equal to -2. There are exceptions. But this is not one of them. The exceptions are OF2, where fluoride is more electronegative than oxygen, but oxygen is actually the second most electronegative element in the periodic table. Because it is the second most electronegative element in the periodic table, unless it is paired with fluorine, then it is going to have a -2 value. Only in oxygen difluoride does it actually have a +2. But aside from that, it's -2. Oxygen is -2. Generally, nitrogen, unless paired with anything more electronegative than it, which is going to be either oxygen or fluorine, because nitrogen is essentially the same as chlorine, nitrogen is generally, aside from those exceptions, equal to -3. The halogens when paired with less electronegative atoms equal -1. And the halogens are in general more electronegative. You stick oxygen with bromine, that's different. Bromine is less electronegative than oxygen. And remember, you don't have to memorize these numbers the way that I have them stuck in my head. I'm going to give you that electronegativity. You won't have to remember this as far as the electronegativity goes. These rules, you have to remember. Electronegativities, you don't. Okay? Fewer things to remember. For compounds with more than one nonmetal, the electronegative an element has the negative oxidation number. That is on page 7. Okay? The compounds with more than one nonmetal element, the more electronegative element is the one with the oxidation number that's negative, and the less electronegative element has a positive oxidation number. The sum of the oxidation numbers in a compound is neutral, and the sum of the oxidation numbers in a polyatomic ion must be equal to the charge of the overall ion. I'll show you some examples now. Okay, so for example, CH4. Here's how we do this. The oxidation number of carbon, well, we don't have to figure that out because What we actually do know is the oxidation number of hydrogen is equal to what? In general, +1. I mean, you had a 50-50, but it is going to be +1 in general. Unless it's paired with a metal, it's +1. Now we can do some math. Carbon plus 4 times +1 must be equal to 0 because it's a compound. There's 4 hydrogens, so each one of those is a +1. Therefore, carbon is equal to not positive. If you do math properly, it won't be positive. You can see you move the 4 to the other side, you end up with -4. Therefore, carbon is -4. Okay? Well, what if we had H2O? This is redundant. We know that oxygen is, in general, -2. We know that hydrogen is equal to +1. That math works out perfectly. Hydrogen, 2 times +1 plus 1 times -2 is equal to 0. That's a compound. It works out perfectly. These will always work out perfectly. Okay. Finally, a good example, a good example would be something along the lines of, where do we go? We go with a classic. Oh yes, an ion. PO4 3 minus. Oxygen is going to be equal to. Exactly. See? Boom. Got it. Oxygen's -2. So now phosphorus we don't know, but we need to add to it 4 of -2, and that must be equal to a total of -3 based on the charge of the ion. So you do the math, you go phosphorus -8 equals -3, so phosphorus is equal to +5. There we are. Okay. Does this make sense so far? I've always found this very nice, actually. It's very logical. Okay. Now, are you guys comfortable with these general examples? There is practice on the third sheet. The third sheet, though, is about recognizing reactions. So let's talk about that. I'm going to show you 1 or 2 examples of reactions, how to track that with oxidation numbers, and then we're going to call it a night. Okay. Here we go. Here is an example of a reaction. Okay. H2 plus O2 giving you H2O. Okay, to begin with, this isn't a balanced reaction. Well, okay, so what do we do? I put a 2 here, and I put a 2 here, and it's balanced. Yeah, I raced through that. Okay, yes, I know this reaction, but you can see how it works out. 2 times 2 is 4 for the hydrogen. 2 times 2 is 4 for the hydrogen on both sides. 2 oxygens on one side, 2 oxygens on the other. Boom. Some of them can be that simple. All right. Question? What page? Oh, this isn't any page. This is just examples I'm pulling from my head right now. Am I crazy? Absolutely. Crazy good. Crazy talented. Crazy gifted. Crazy brilliant. Okay. Oxidation numbers. The oxidation number of hydrogen on the reactant side is. Pardon? It's not classified and not +1. It's pure, so it's 0. It's by itself. If you're lonely, you have nothing. If you're by yourself, you've got nothing. You've got no one. 1 is the loneliest number that you ever seen. No, it's not true. 0 is even more lonely. Oxygen, therefore, is also equal to 0. Okay? Now, over here, it is. There we are. Exactly. Here, hydrogen is equal to +1. Here, oxygen is equal to -2. And if you forgot one of those rules, as long as you have one of them, you can actually back calculate the other. Because 2 times +1 plus 1 times -2 must be equal to 0. It's a compound, it must be equal to 0. Okay? Now, look at the change. Hydrogen goes 0 to +1. Oxygen goes 0 to -2. So, what is happening to hydrogen? Has it gained an electron or lost an electron? It has lost an electron. You've lost an electron. You've lost a charge. This is like a credit card. When you lose a charge, something becomes more positive. You lose a negative charge, the oxidation number becomes more positive. Oxidation number, this is your oxidation credit card. Tracking negative charge of electrons. This is your oxidation credit card tracking negative charge of electrons. So when you lose a negative charge, you go up. Here, you've gone from 0 to -2. You've gained electrons. So loss of electrons, this is oxidation. Gain of electrons, this is reduction. Okay? I wish I had time for net ionic equations. We don't. I'm cutting myself off at 9:45. We're done. Okay? I will try to record more stuff tomorrow. Please come to office hours if you can. Please have a good night.